Can everybody see that all right? Right on. So today we're going to be talking about the camera. This shouldn't be a huge surprise given where we've been kind of moving this semester, talking about digital culture, the fact that digital culture is highly visual, then doing a deep dive into how we see and perceive, and starting to move towards systems that are totally inorganic, right? And so we're going to look at a number of things today. We're going to touch on some of the discussions of color that we've already had, and just do like we do every class, a little review. So last time we met, we talked about color production and this kind of model of color in which there's a relationship between incident light, the surface that's reflecting that light, and then a bunch of other factors. So can somebody remind me what incident light is? Like, what does that mean when I say that? Yeah, it's the light source, right? And what are some things in terms of incident light that interact with the perception of color? What were some of the phenomena that we spoke about? Manning? Huh? How would heat do that? Like warmness and coolness, is that what you mean? So the Kelvin? Yeah, like blue versus red. Yeah, absolutely. We talked about like a specific phenomenon. Were you talking about heat that way, or did you mean like literal Kelvin? Okay, right on. We talked about a very specific phenomenon in which heat, or now I'm saying it, in which warmth of light can really make a difference. Yeah. Albedo effect? Albedo effect is how much the stuff is reflected, right? So it's that reflectance value. We talked about metamers. Remember that? Yeah. So one of the things that we covered that's very important was this idea that color is like a kind of a composite. It's like a chord in music. It's a bunch of wavelengths coming together. And then also, because of that kind of broad chord, that it's actually a little more complicated than it seems to us. Things don't usually come to us as spectrally pure, that thing is yellow because it's only reflecting yellow light. So we talked about the idea that there's a lot of spectral mixing that goes on. We look at this banana and it does appear to be yellow, but that's not the only color that's being reflected, right? Next, we kind of thought about an equation or a formula for determining color, which is that incident light, its warmth, like Manning and Evans said in terms of Kelvin, blue or moving towards a red-green, multiplied by that underlying chord or the reflectance value of that object. You multiply those two things together and you get like the final color that you perceive. Does this make sense? Any questions thus far? I need us to be like very comfortable with this idea that color is a combination of multiple factors and is definitely something that will be on the midterm oral exam. Right? You can expect to sit in my office or out in the rhetoric studio and I'll say, let's talk about color, right? And these are the kind of things that you'll have to be able to articulate and we'll go from there. So if I can correct any questions or kind of hesitancies we have now, I'm happy to do it. And remember, all of these are recorded and hosted to YouTube too. Not that you have better things to do than listen to YouTube lectures. Yeah?
So when you multiply the incident light times, like this says primary blue, how do you determine what you multiply it by? Like that primary blue, is that just like what you do every time, or is that what you see?
Okay, so the final spectrum is what you're seeing. The incident light we measure with Kelvin, right? And the actual spectral frequency or wavelength, that's like, there's a whole kind of discipline called spectroscopy where they try to figure out that exact thing. And in fact, if you know the spectral frequency for that thing, that object you're looking for, you can design sensors that just go and get that. I have a colleague that does that for like detecting mines, right? Like the metal in a mine, not like down in the ground, but like blow you up kind of mine. It's a very specific kind of metal. It has a spectral waveform that is unique. And so you just design a sensor that goes after that, right? Whereas when we're talking about the camera, we're talking about this thing that approximates the eye and is picking up a large range of things. But you could think about designing a camera system that is only going towards the one thing that you need to see. A lot of times, that's kind of the underlying idea behind hyperspectral imaging. Hyper meaning more than one spectrum. And since light is a wave, that's kind of a chord, that kind of makes sense why we call it that. Does that answer your question, Manning? You following me? Yeah, okay. You were looking intently at me, so I didn't know if you had a question. So, of course, yeah, we discussed metamers, and we looked at metamers as this example where we get the same perceived color under similar incident light, but the underlying waveform, or that kind of here in this primary blue, we're talking about that part of the equation, it is fundamentally different. So thus, when we change the incident light, we get a perceived change in the color of the object, right? We talked about the blue and gold dress as an example of this. And metamers are complicated in terms of like ensuring that in certain applications you have a consistent color experience for the end user, but they're actually pretty interesting too because they get at the idea that we can take basically red, green, and blue and make a lot of different colors from it, right? This, of course, is not red, green, and blue. This is referencing your short, medium, and long cones, which we talked about quite a bit in terms of that. They actually cover a little more than just red, green, and blue. And we have 3 cones, and then we have 1 rod, and we have 1 type of rod. What do the rods do? Huh? Night vision. Low light. They can come in and kind of break the tie in some instances if you're not sure about what color, your eye's not sure about what color. And then we talked about, okay, so we have these short, medium, and long cones. How do we actually make a model of color that we're using like when you get on your phone and you get on Instagram, right? And we looked at this trilinear mixing triangle, which is pretty old. And basically, in this triangle, this is your short, your long, and your medium. If you're up right here, you're only activating the short cone. If you're down here, you're only activating the long cone. Anything along this line is a percentage mixture of short and long. We understand how a triangle works geometrically. This white point in the middle, what do you think that means?
The equal amount of small, medium.
Yeah, absolutely, because white is a combination of all colors, right? And black would be like the absence of that. Okay, so yeah, equal participation is even on the slide. Hey, I like it. Participation doesn't matter if it's you're coming up with the idea or you're just reading out the slide. So then we thought about, okay, so you take this kind of triangle that's based on rods in the eye, and how do you translate that into a type of color that you can reproduce digitally, like when you get on a screen and you look? And we talked about a French organization called the CIE, which did a lot of work to try to standardize color. And what they're trying to do here is have like a mathematical function that can take what your eyes typically are able to see in terms of short, medium, and long, and give you the ratio of red, green, and blue that you need to mix in like a television screen or an LED device so that you're seeing perceptually, as long as your short, medium, and long cones are the way that most people's are, you're seeing what kind of the author or the computer scientist or the tech bro wants you to see, right? So we know that based on experience that people do have similar color perceptions, and the question is, how do you ensure that consistent user experience? The last thing we talked about is that there are kind of some trade-offs in terms of the total range of color that you can see. You can do a lot by mixing red, green, and blue pixels together, but you can't come to that entire triangle. And so a lot of different companies have designed these things called color spaces where they're trying to maximize the user experience to see as much of the spectrums, and there's a no free lunch principle there. Do you know what I mean by no free lunch? Lunch is never free. This is a concept we're going to come back to again and again in a lot of topics. It's seen in machine learning, but you also see it in economics quite a bit as well. Some of your economics professors might talk about this at some time. It's the idea that as you get a solution to a problem that's specialized in any given direction, it's worse at all other things. It sounds simple, but I want you to think about it. As you design a solution towards one thing, that specialized solution gets worse at all other things. Thus, no free lunch, right? Can we think of an example of that? It doesn't have to be mathematical, just in life.
Focusing on like one class to study for, and study for your other ones.
Yeah, there could be like a zero-sum game in terms of the time you have. What about you need to cut something, right? You have a knife, right? That knife does a really good job at cutting it. Why did we develop scissors? Like as a species. They also cut. Why develop scissors? Better at cutting very specific things. But the kind of specific things that you can cut with scissors often lock you into not being able to use a knife. I mean, you wouldn't try to like process a deer with like barbershop scissors, right? You're starting to understand this idea of no free lunch. And we'll see this again and again as we start looking at very specific solutions to things, that the more specificity you have in a solution, the worse it's going to be to a more generalized problem. And if you take anything away in this class, maybe the no free lunch theorem is something that should always be ringing in your head as you're sitting professionally moving forward and you're listening to a team discuss different options, right? Not everything is a zero-sum kind of no free lunch game, but certainly color is, right? Because as you pick one of these, you're less able to do everything else. All right, so then we talked about we ended class talking about, well, how do we use this? I mean, color's cool. I think it's trippy. I think it's fun to think about. You definitely learn a lot about your eyes. But why are we covering this? And this is what we're going to jump into a lot today, is that, well, in a digital culture, we need to be able to consistently take the colors that you perceive with your eyes and translate them into a mediated experience. If we have no consistency there, well, then you don't have really a medium that is able to project digital images in a meaningful way, right? It starts to lose its importance if we're seeing different colors based on a variety of factors. All right, so I want to start kind of with a 1,000-feet overview of like where are we moving in this class, and then after I show you a couple examples, I'll go ahead and we'll start building it from the ground up. Right? We're not going to get all the way to something as complicated as this today, but we will start to get there towards spring break. So this is just an example of why we start talking about like the granular things like color, light, what a pixel is, because in today's society, we use computer vision quite a lot to do things. So this is one of my UPIC colleagues. This is a photo I took of him when we were out on a project where we're putting out these buoys that basically tell you your wave height, and he's hunting because they hunt, right? And this is an example of something called an object detection model. So here I'm detecting that it's a rifle. I have a confidence interval that basically the algorithm is telling me it's 94% sure that it's a rifle. And these are just kind of the evolution of object detection models over the past 10 years or so. Right? Object detection is a huge part of underlying computer vision and artificial intelligence today. Has anybody ever interacted with an object detection model before? Yeah?
Yeah. For our project.
For your project, absolutely. But what about in real, like outside of the project that we're working on, when have you come across an object detection model? I'm sure Walmart, yeah, I use that example. Any of you, I mean, they're all around you. And now that you start looking for these are called bounding boxes, you'll start seeing them more frequently, right? They're a huge part of many things, including self-driving, theft protection, like biometric passport scanning, things like that, people detection. You can start to think how applicable it is in modern society. I remember doing some research a couple years ago, thinking about, I was kind of really interested in these concepts, and I was thinking about applying them to satellite imagery. And a big use case here is being able to find those big shipping containers, like the big ones that impact trade in the Panama Canal and these international kind of political relations, that you can track them with object detections out on the sea. Why might that be important? Like for our econ and business people. Did you quantify like the amount of trade you might have, and then be starting to think about what countries it's coming from and knowing if maybe there's a port shortage or something like that. Absolutely, there's incredible intelligence applications here. Yeah, object detection is part and parcel of the experience that we have. There are people who think very specifically a lot in like econ, business, social media, intelligence about using them, and then regardless of whether or not you're aware of them, they permeate your experience, right? They're a type of classification algorithm that is very dominant in today's society. Ned, look, they got a question or comment?
It was about like the Walmart, like where we see object detection. Like,
Yeah.
Don't you also see that? Like I see it sometimes at like TSA and like an
Yeah,
airport.
yeah.
Like what you're saying about the passports.
Mhm.
Like I put my passport, like put my ID in it, like I don't know, does it like check the ID with my face?
Yeah, there are a lot of different ways that we do like biometric scanning. Not all of them are drawing a box around the object, but absolutely yes. How many of you know someone who has like a Ring camera, right? There's a good object detection model in there as well for recognizing people. Yeah.
QR codes also be, is that like?
QR codes are a little different. They're not detecting an object. It's just basically a way to use the camera to access URLs. But it does have some underlying computer vision. Barcodes in general are this intersection between data and vision. Yeah. Another example that we'll get to is image segmentation. So this time we're not drawing a bounding box around the thing, but we're trying as best as possible to say what the phenomenon is, in this case a human, and then draw a clean mask around that human. We see this in things like Photoshop all the time. This is one that is very important if you're going to use optical systems for self-driving. You want to mask people that are moving so you don't hit them when you're driving. On the syllabus, and one of the things in participation credit today, on Thursday when you start taking pictures, I'm going to have you take a picture of a person, and then you're going to run this algorithm. And we're going to all be together. The computers will be out in case you hit barriers. But you'll see that it's about 30 lines of code these days, and you can do the same thing. And one of the things I want you thinking through with final projects are like, okay, so you're an econ business major. How can an algorithm like this be useful in the real world? Because I will tell you it is, and a lot of people make a lot of money thinking through these problems, but a lot of times we're not even aware that this exists, or we don't even understand how it works. We're not able to like become part of that kind of discourse community or think about such selections. It's not that everybody needs to be a coder in this class, but sometimes you have to understand the trajectory of digital culture and that it's not just all social media. That, in fact, a large economic driver of our current system is computer vision, right? There's a reason why like Meta is a very, very wealthy company that has very little to do with Facebook. All right, so before we can understand how these work, because these are kind of complicated, they're like neural networks, some of them like SAM, segment anything model, is a transformer network, which is the same type of network as like a ChatGPT. There's a lot there. We can't just dive right into it. The first thing we have to understand is, well, what is an image? So we went from the eye to vision, and now we're looking at what a camera is, and by extension, what an image is. So great slide here from a series of lectures I've linked on the syllabus. This is, I think we've talked a lot about the eye in terms of rods and cones, but we haven't really talked as much about it as a type of camera system. And a lot of people do think of the eye as a type of camera because as that phenomenon out in the real world the light is coming into the eye, it's being projected in a way that is very similar to a modern camera, right? Can anybody remind us when we talked about the eye, what are some of the things that we've evolved to be able to have like a quote-unquote better eye from the original eyes? What were some of the first eyes?
They were just like pads.
Yeah, and what was the problem with just having like a photosensitive patch? There's a specific word, it started with an A. I'm going to give it to you because, yeah. Acuity, yeah. And what does acuity stand for? Like, what does that mean?
You don't know, like,
The direction.
coming in from?
Absolutely. And then so we went from the photosensitive patch to what? What's the next kind of evolution? Pit eyes, right? Because you have some sense of acuity, right? If you ever been in a cave, right, and you see the sun, you can kind of start to determine direction. And then we develop all of these things like corneas and lenses to get to a point where we can control the amount of light that comes through. We can open basically the aperture or the hole in terms of our eyes so that we can manipulate the acuity. And by God, that's what a modern camera does, right? And so the first cameras that we came up with were pretty simple, and I probably discovered by accident, to be completely frank. There is what is known as a pinhole camera. Has anybody made a pinhole camera before, or you're aware of the concept? You're like, if you're not, you're like, middle school art teachers let you down, right? This is a pretty simple apparatus. It's a box, and there is a hole in it, and the light comes through, and the hole is small enough that you have a good amount of acuity, and then you reproject the image just like you do with the eye. And this is something that has been known for quite some time, right? I said like the first ones were probably invented by accident. Because we can go all back to ancient Greece and see that people were aware of this phenomenon. If you have a small opening, or what we call an aperture, you get this, if the light is the incident light and the angles of geometry are correct, you will get a projection of the image if you have a good, what we'll call a sensor in the background. In this case, it's just a wall. And so cameras obscura, before the age of digital cameras and film cameras, there were still cameras, and they were these kinds of cameras. Pretty simple, sometimes by accident. And if you really stay in tune with life, you'll notice that sometimes just around you, there'll be a camera obscura effect, right? If you have like a small window or maybe a slight crack in a wall or something, and a little bit of light streams by, you'll be able to see a projection of what's going on the other way. Questions, comments? Is this making sense so far? Good. So the camera obscura informs a type of photography, a type of early photography known as pinhole photography. And what we're doing here is we have our rays of light from our illumination source or incident light. They're hitting the object and then moving through that small aperture, and you'll see that the projection is inverted, right? And this is very similar to what an eye does, and there's a certain focal point or a center point in that image, and that is the only thing that is not inverted. That comes straight through here, okay? And if you want, I mean, you can build a pinhole camera for this class as part of your project if you're really feeling it. And the image here that's being inverted with everything except for that central focal plane, that's known as the image plane. And we're going to do a lot of work with the image plane this semester. Not surprisingly, this hole right here that lets light in, that's known as aperture, and that's pretty important. There are some interesting things that happen as you open or close the aperture. Before we get into it, what do you think that relationship between aperture and the image plane is? What do you think happens as you open it? More light gets in. Like sometimes we got to just start at the most essential things. Thank you, Jabal. More light comes through. Absolutely. What do you think that does?
With the more light, there's depth, right?
There is a relationship between the depth of field. Yes, absolutely. You've played with some cameras before. What else? This is, I'd be a little surprised if anybody was able to just organically put this together. It's not quite intuitive, but by the end of class, I think it will be. So in order to understand that relationship between the size of the hole in the pinhole, and which we call in photography f-stop, and what we actually get as an image, let's look at a very simple example. I've hyperlinked this source. This is cool because they take an actual camera and they just make a pinhole camera out of it by poking a hole in front of a lens cap and letting light in. And this is kind of what they see. This is something we could do on Thursday if y'all want. I can drill one of our lens caps and make a camera obscura. And you can't adjust the size of the hole or the aperture here, right? Now, f-stops, how many of you have, you've shot a shotgun, or you know someone who's got their ears pierced, or you've worked with electrical wiring? Okay, those are all in gauges, right? So a bigger gauge means what in terms of a shotgun? If it's a 12 gauge versus a 16 gauge, which one has the bigger shell? 12, right? So these are in gauges. So don't get it twisted as we go through today. As the gauges go up, it means the aperture is smaller. That's a unit of measurement that we always use. In fact, needles in hospitals are the same way. You want a higher gauge needle, ideally, for your personal lack of pain. But we see here that this image, there's a fixed aperture or a fixed f-stop. The gauge of that hole is, you can't adjust it, unlike our eyes, which open and close with the amount of light unless you're on some drugs, and then sometimes your pupils dilate or don't dilate. But your pupils are an aperture, right? They're this in the pinhole model. Why is this blurry? It's not focused. Yeah. What were you going to say, Ned?
I've taken a photography class before, so
Good.
I feel stupid like
Yeah.
being able to tell.
Did you cover some of this?
Yeah, I mean like we went over aperture and like focal points, like everything like that, but like I cannot remember. But,
Yeah.
Is it like the more aperture, like is that like when you're twisting the lens, like is that what aperture is?
That's focal length.
Focal length.
Aperture is like, think about your eyes. It's like
in
squinting
focus.
your eyes or opening your eyes. Or when you go from like a really dark room where your pupils are big and then you step in the sunlight, your pupils shrink. In fact, that's like one of the things that cops look for, like on a really dark night where your pupils should be big and they're like pinpoint, right? They're going to look for opioids. Conversely, if it's really bright out and you have pupils the size of like saucers, they'll look at other types of stimulant, or they'll look at stimulants, right? So there's something going on there. Yeah.
Is the pinhole too close to the sensor? Like if you
It has to do with depth of field and pinhole train-off. You're getting there, right? So we talked about this being the center point. This is the image plane. There being the light is coming in. That basically, if we can center the smaller the aperture, and remember our lectures about the eyes, the more we're able to center that phenomenon there. We're kind of bringing things together, which is going to put them in focus. The larger the hole, well, then we have less acuity, right? It's no different than the eye. Things are going to look more blurry. Does that make sense? Because I know we went from like I don't understand it to hopefully now it makes sense. You're looking confused, Manning.
Yeah, a little bit.
Yeah.
You said so the larger the aperture, the more blurry.
Yes. Yeah. Generally, yeah.
Okay. But why is it when you squint? Wouldn't that be lowering your aperture so it's more, but then that's
Okay.
more blurry?
Remember our discussions of the eye, right? That as we went, and I wasn't just because I like eyes and I have some kind of like obsession. It's like my hyper focus. It's that it actually informs a lot here. Okay, so very little visual acuity, more visual acuity, even more visual acuity. And then in the modern human eye where we can change that pupil, crazy amounts of visual acuity. Does that look pretty similar to that? Right? And so the smaller that we can constrain the aperture, the more visual acuity we have. And in terms of like a visual phenomenon, it's kind of weird to be like, well, it would have been really blurry with the eye patch. But I mean, in a way, it kind of is, right? And then with the pit eye, you can get a general sense of the direction. We're working towards a kind of like resolution, if that makes sense. So as we constrain the aperture here, and we see this here at 2 millimeters, at 1 millimeter, at 0.6 millimeters, and 0.35 millimeters. So as our aperture increases, because remember it's inverse because it's like a gauge, that we're getting better visual clarity. Does that make sense? Yeah, it's the kind of thing is like does once it all kind of comes together. That's why we started with the eye. Because if we hadn't started there, I think we could have spent an entire day talking in circles about why that relationship is. Yeah.
The inversion inverse, but I mean, it makes sense like, when you think about it. Just because, like, in your own life, like, when you are squinting your eyes, like, or, like, you're...
The inversion on the image plane, you mean?
Yes, yeah, like, or also the inversion, like, technically, you feel like you're increasing the aperture by going to, like, f/22 or whatever, but it's actually, like, just the way the camera works, like, you're going down.
Oh yeah, there's a ton of kind of rules of inverse with light,
Yeah.
but I mean it's really basic geometry, right? We have like a law of triangles here, that we're getting an inverse triangle based on that relationship between incident light and then the aperture. So this is my pinhole camera maybe, right? Yeah, absolutely. It's these things that they're simple, but they're very complicated at the same time. And you start thinking, well, why is it inverted? Well, because we have like a law of triangles here, right? Why is it get more in focus the smaller the aperture? Well, on the one hand, it makes no sense, and then you start thinking about the eye, and it starts to make sense. Yeah.
Does this have anything to do with like if your vision gets worse and glasses and stuff?
Yes. So there can be different reasons why you're short-sighted or farsighted, and then you also have stigmatism. So stigmatisms are that the eye is just a little more misshapen. I have a stigmatism in one of my eyes, and that means that because of that, the way that you can flex the eye, because to focus in, it's not like we put on a different lens on our eye. We literally change the shape of our eye a little bit, which change our focal length and aperture. I want you to, we haven't covered focal length, we're about to do it in 5 minutes, but basically that's how we manipulate the eye like a camera, and on a camera we just switch out a different lens. So yes, it does have a relationship. I would say that in terms of aperture, you can, probably the better example here is not farsighted or nearsighted. It's that relationship between when your pupils get bigger or smaller. And so ideally, if you're not on drugs and you don't have something like Arnold-Chiari syndrome, which impacts your dilation of your pupils, that your pupils should basically be scaling themselves depending on the incident light out there to basically get as small of an aperture as possible for the highest amount of visual acuity, while at the same time letting enough light in that your rods and cones can work. Does that make sense? Because if we, I don't want to give away the lead. So why not make the thing you could say is why not just make the aperture as small as possible then, right? If we know that you get more visual acuity as you make that hole or the aperture smaller, or the f-stop increases because it's a gauge, why not just make it fucking tiny? Then you have really clear. Well, two things. One, less light comes through. And remember the human eye, the rods and the cones, the digital camera is no different. Like it does need some light in order to do its thing. So it can't be that you just constrain it to the tiniest hole. And the other thing is that there is, as the aperture gets very, very small, you will start to get blurriness again because of something called diffraction. Which we don't need to cover ad nauseum. I just had a couple examples of this. So this is in terms of f-stop, like a shotgun shell gauge, and f/22 is much smaller than f/2.8. You'll see it gets, this is kind of your good spot in terms of clarity, and then you start to get a little vignetting and these kind of rays. If any of you wear glasses, sometimes you get a similar experience at night. And then this is showing you that you do get clearer as you go to 0.35, but as you get smaller, you start to get blurry again. So it's not that we can just make the aperture in our cameras as small as possible, because we do still need to let in incident light, and there are some geometric ways in which at a certain point, as you constrain that beam, you'll get to a point where you constrain it too much and it starts to kind of blow out, I think would be the right term. Yeah, so why smaller isn't always better? Because remember that light is a wave. So when waves are forced through a very small opening, they kind of ricochet a bit, right? And so we can get to a point where we make it smaller and smaller and smaller, and then at a certain point, it's going to diffract or bend because it's spreading those waves in kind of unpredictable patterns through our medium here. This is why we talked about diffusion a couple lectures ago. Yes, Ashford.
I'm curious, so if we make the aperture like so small or so big, it like if it's focused, it changes if it's focused or not. But like when when I use like a really big hole on the camera,
Mhm.
it just looks nice. So what else
Yeah.
like, affects the sharpness?
A whole triangle. A triangle of how much light you let into it, right? How far away that thing is in terms of like your focal length and your aperture. We're going to cover this on Thursday, but it's called the exposure triangle. And it's not something we cover too theoretically because I'd rather just show you on a camera. I can get you all to learn it in 6 or 10 minutes that way. Questions or comments? 5 means this makes total sense, it's not complicated. Fist means this is a little harder than I thought it was going to be. Where are we at? 4? Okay. Good. I like the fact that we're at 4s or 5s, even though when we start every one of these little sections, we're probably at 0s. That's maybe the point of teaching. And then taking a really obscure text like this and translating it into a way that makes sense. Okay, so the next step, obviously, well, maybe not obviously, but at some point you might want to be able to constrain that aperture in a variable way. And depending on how much light you have and how far away your thing is, you might, just like the human eye, be able to change that. And this is where we started developing lenses. Now lenses don't just do aperture, but aperture is a pretty big part. There's like a bunch of blades in your lens that open and close it just like your pupil. So you can kind of find that sweet spot. And different cameras have different kind of ranges on what they're able to stop up or down to, so how big they can make that. And that impacts a lot of the work that we do, right? Like a lot of phones do not have the same kind of aperture range or things like that that a fancy camera does. I don't know if it's still the case, but for a while, iPhones were just stopped at 2.8. That was the aperture, it's a fixed aperture. And so they're having to do other things to bring things into focus. And so the lens focuses parallel ways. We got this boat here, and we have our focal point, we have the optical axis, and the only difference now is that we've put a piece of glass in front of it, and that glass has basically the ability to open and close the hole in terms of the amount of light that gets in. And so now we can really we can constrain some of the things that might happen here by just opening and closing it. Oh, Jake needed something. Yeah, a marker. That's why you gotta have PowerPoints. All right, so definitely lenses focus light, but it's not just about how much light they let in or out. They can also change the focal length. And now I'm dropping a new terminology on you. And we're going to cover what focal length is in just a second. So the lens takes parallel rays and it basically focuses them into a certain point. And that distance between the lens and the center point on the image plane is our focal length. And typically, we measure that in millimeters. So 50 millimeters, 200 millimeters, 18 millimeters. And do you think that has any impact on the focal length has any impact on the way that the image looks? Raise your hands if you say yes. Raise your hands if you say no. Okay, yeah, we're intuiting pretty well, but we might not be able to say what the relationship is quite yet. Does anybody, besides maybe Hayden or Ashford, who I know work with cameras, does anybody want to just take a guess at how focal length might impact the image? Hey, I mean,
Shorter the distance, the more focused the object is?
yeah, there's a relationship between distance and focus, and I will put it this way. How many of you have looked through a telescope or you've looked through binoculars, right? Are you changing the focal length there? Yeah, many of us are shaking our heads, but you're not really sure why, right? That there's, in terms of the range of what you can see in an object, right? Focal length is going to be important for basically how zoomed in or zoomed out you are. But before we get into all that, let's just talk about some early lenses. Because sometimes, if I start with the eye here, I want to start with like non-digital applications of cameras, kind of build it up from the ground, so to speak. This is a big like terms of the way I teach. This is how I like to do it. We break it down Barney style. We're going to start with simple things, then build it up. Because some of the stuff we're talking about is a little complicated. So, the lens-based camera obscura has been around for much longer than America has. And not surprisingly, people figured out pretty early that the pinhole camera is great, but if we could have a little bit more control over that aperture and that focal length, we can basically focus on things a lot better, right? We don't have to just like drill a hole in and then be like, oh, yep, the incident light doesn't let enough light in and things are blurry. And then there's a relationship between how far the person or the object is away from the pinhole camera in terms of how that light is being centered, right? So people figured out pretty early that what we needed to do is we needed to be able to change not just the aperture, but the depth of field of focus. And this is something that we will see on Thursday quite a lot, that these fancy things on a camera that you see sometimes, you got a friend that's into photography, you have no idea what these things are, that these are basically allowing you to manipulate aperture and focal length to a certain degree. This is your aperture ring. It's in terms of f-stops. So this is going to be a smaller hole, and that will be a larger hole. And then the depth of field indicator is actually pushing, making the focal length in terms of the lens shorter or longer. And in cheap cameras, you literally see the lens like move out or move in. So depth of field has a huge impact on what's in focus. And so the changes in aperture affects the depth of field. A smaller aperture increases the range in which the object is in focus. So another way to put this is that the smaller the hole is, the more that everything in the scene that you're taking a picture is, everything's going to be in focus. The larger the hole, the more you're going to kind of center on one object. So we have a good example here. Large aperture, only the flower is in focus. Small aperture, everything is in focus. And in fact, this is something that artists use quite a lot. I want you to go watch some TV. Go watch a trashy reality television show tonight or a movie, and you'll notice that this bokeh effect, where you subconsciously use a larger aperture, larger hole, like 2.83 instead of 22, will bring just the subject into effect, and you see that in television so much. If I'm interviewing you in a scene of people, I want the viewer's eyes to just be focused on you. And so you'll catch this all the time. In fact, a lot of cinema cameras that we use like for shooting Marvel movies, they're fixed apertures at 2.8. So it's really just what's in front of them that's in focus. And then other times, folks will go with a smaller aperture like f/22, smaller hole to kind of bring the whole scene into focus. So depth of field. And we can see why this is the case, right? We have our focal length, we have our aperture, and then we have a focal length on the other side. So the larger the hole, the more our image plane is going to be centered just on what's in front of us. Focal length, so aperture is the size of the hole. Focal length is how far away that image plane is from the aperture, and we talked about in a lens you can manipulate that by putting different lenses in front. That has a pretty big impact on our field of view. So what is actually visible, and this is why I talked about a telescope. A telescope allows you to magnify in quite a lot. It changes our field of view to a very narrow part of what you could normally see, right? It's because it's a different focal length than your eyes. Questions or comments about that? Is that confusing in any way? I like this example. So this is the same picture, exact same picture. We're going to look at two slides here. It's just different focal lengths, so different ranges in terms of millimeters of these lenses. So 17 is really wide, and so you get like this whole scene. And as we stop up towards 25, 50, we get less of a field of view. Do we see that? And this what's trippy about that is like this is the whole scene, and then this is at, let's see, 1,000 millimeters. So you get just focused right there on that tiny little piece of the boat. Yes?
So because these are projections and we're making it all onto the same like rectangle,
Yeah.
the 17 looks weird, right? It's like all stretched.
Yes, there's a
Just, like,
distortion. Yeah.
Put it on an equally stretched like screen or something. Would it
Yeah,
be
yeah,
more
you could
natural?
try to compensate by having it. I mean, we even have a keyhole effect here if you look. There's like a slight blur. This is not something I cover in the lecture because it's like a very kind of specific, but there are, lenses aren't perfect. They introduce radial distortion and chromatic aberration, and basically some of those we can't fix, a lot of them we can, and the camera just does that behind the scene because people are really good at math and thinking through things like this. Does that make sense?
Yeah.
But it's no free lunch there. Lenses allow you to change your focal depth, and modern lenses also allow you to change your aperture, which is great in terms of being able to have like an eye, so to speak, that is like just as good as our eyes, sometimes even better, but no free lunch. It does come with some types of vignetting is one, radial distortion, which is what gives you the fisheye effect here. You see how this kind of, what he's talking about here is how this kind of seems like distorted right here. If you ever watch like old skateboard videos, if you use a really wide angle lens, you get this kind of trippy, everything's kind of circular. So there is a relationship between our field of view, what we can see, and our focal length. And we can adjust the focal length with both the aperture and the distance with the lens in terms of millimeters. It's the exact same distance from the car here, but it's just one seems closer and one seems further apart because we're manipulating the field of view. Now, this is cool for art. It's cool for TV. If you're taking a photography class like Ned is, that's awesome. But for some of the things we'll do in terms of like thinking about digital culture, this is also really important if you're going to build like a people detector, right? Because you can do some pretty trippy things, and maybe I'll give you an example of that. This is the same face. This is why people say, oh, the camera adds 10 pounds, right? Same face, but looks quite different based on the field of view. So a real wide angle field, this lady looks way different than she does with a telephoto lens. Does that make sense? What would be the focal length, do you think, in terms of, let's say this is between 1 and 100, right? Which focal length of these three, left, middle, or right, do you think is a focal length more akin to like 10? That's the other one, right? Yeah, yeah. The number goes up as you zoom in. Yeah, think about your binoculars. Yeah, yeah. Yeah, it would be nice if it wasn't inverted, but like everything with cameras is for some reason. It's turtles all the way down. Yeah, so if you want to make somebody look skinny, shoot them with a telephoto, right? If you want to make them look a little bigger, shoot them with a wide angle. And that makes sense, right? At a wide angle lens, something like at 15 millimeters, 17 millimeters here, we're letting our ability, that focal length is a lot shorter and wider. And then as we push forward with a telephoto lens, a zoom lens, we're constraining the field of view, but allowing the focal length, the distance between our aperture and our image plane to increase as well. No free lunch. As you're able to increase that length, you're dialing in the field of view. This is the mathematical equation for it, and I referenced this earlier. Like, we have a lot of just like very simple geometry that's happening, but again, we don't need to really deal with that in this class. This is, if you see this in the assigned reading and it doesn't spark joy in your life, just skip it, right? If it's something I feel like you need to know, we'll cover it in class. So, and I say that as a preface to talk about this slide, which is mostly for I think. We can obviously mathematically model all of these things we talked about, and we do it with some nice linear algebra. And what, if you're not into math, what I need you to take from this slide is that we can view the image as a mathematical function that takes 3D space and projects it into a 2D plane. It eliminates a dimension, right? So on a Cartesian coordinate system, x, y, and z, we're getting rid of the z, and we're just giving you x and y. And that is great in terms of having a phenomenon that we can view on walls and stuff. It's not great in terms of telling distance for how far away that tree is from that car, right? And a lot of the more advanced work we do is try to sometimes take that 2D image plane and reproject it back into 3D space to capture that distance. That's what like virtual reality and 3D modeling does quite a bit. All right, questions, comments thus far? All right, let's keep rolling. This is fun. Now we need to talk about the digital image and what's actually going on there. So if we know that the relationship between an image, any image, whether it's on film or in a digital medium, is basically light is moving through an aperture with a focal length and then hitting a sensor. The question is, how do we do it with the digital image? Well, we do it in terms of this nifty little thing where we have a piece of silicon that is susceptible to light, and then we divide our image into a series of grids. Pop, pop, pop. This is the number of pixels we have, and within each grid, we give it a intensity, right? And a grayscale image, black, means that you're not adding a lot of light here. You see it's 26 down here. We're zoomed in right at this point in his jacket where we get the background and the jacket, so we can see literally that's literally what this is. So if we have a lot of light coming to this grayscale image, like in the sky, the pixels up here are closer to 255. We go from 0 to 255 because of some computer science stuff called bits. You multiply three-dimensional image, red, green, and blue by 255, 255, 255, you get about like 14 million. Our eyes can see about 2 to 3 million colors. So we have enough like information to store. If that just seemed like googly to you, that's fine. For some of us, I need you to remember that. That's why we can do it either at 0 to 1. Some indexing systems are 0 to 1. 0 means the pixel is completely off. 1 means it's all the way on. But a lot of them are 0 to 255. And depending, I'm just going to have like a quiet site. Depending on the computer vision libraries that you use, you need to check that because your code is going to have to be specific. For the rest of us, though, let's join back up. All we need to know is that 255 means a lot. 0 means none. And remember we talked about the color matching experiments is turning a dial. This is a grayscale image, so all we're doing is turning one dial. And in terms of each one of the kind of LEDs that we could have on the screen or that we're capturing the camera is gridded, right? And we're able to just turn that dial to a certain point. And if we do that for every, let's say you're like a little robot in some steampunk world, if we have a image that is 64 pixels, so it's 8 pixels by 8 pixels, you have 64 knobs to turn. You turn each one right, we'll get a little smiley face. Does that make sense? How do you think we decide how many pixels are in an image? What's 4K resolution? We've heard that term, right? 1080p, 4K, 720. That's the width of the number of pixels there, right? And since our aspect ratio and 4Ks are usually, like, monitors are not quite square, they're kind of rectangular, that X or that Y dimension is not going to be 4K as well. It's usually, I think, like 3,000, something like that. So that's literally when you go to Walmart, you buy a TV, it says a 4K or an 8K or a 1080p. That's all that's referring to, is that on that screen, you're going to get width-wise about 4,000 of these pixels. The more pixels you get, what happens? Clearer you get. Yeah, that's why you get like a 4K television instead of a 1080p television, right? And then it also obviously depends on what that's being broadcast in too. Because if you have 4K television, but you're only getting it's only giving you the information for 1080p, you're not going to have the same visual experience as if the input signal was also at 4K resolution. That is literally all resolution is. It's the number of pixels you have in this grid, right? And different cameras, the sensor is larger or smaller, which allows them to do higher or lower resolution. Does that make sense? Yeah.
So for like in like movie theaters, like IMAX, because that just like is that just adding more pixels on the top and bottom, like getting it clearer and like expanding it?
Yeah. I think IMAX is film, if yeah.
It's very large. There's only 10 IMAX theaters
Yeah.
in America.
Yeah, but yes. So basically, camera that captures it, huge sensor, right? Like big format. Like some like old school photography things, like the camera is literally this big. It's letting a lot of light in. So you have a lot of resolution there. And then you're able to project that resolution natively onto a screen that is able to handle it as well. But yeah, that's literally all that's going on. Yep. So if you've got a new phone and it says, oh, now I can do 6K, it means that in terms of the amount of pixels it has that it can turn on and turn off, you got 6,000 on the width side. And you can see as you, like when I said let's say we have a 64 pixel image, 8 by 8, that's really going to give you some, I mean, there's not a lot you can do with that. You can make like X's and O's and smiley faces and frowny faces, but you can't do this, right? What does this look like if it's 8 pixels, 1, 2, 3, 4, 1, 2, 3, 4, right? Then, or I guess 8 by 8, then you can have basically a blob detector. You'd be like, oh, there's a blobby thing there. Does that make sense? Cool. So, yeah, pixel intensity. We have our rows and our columns. They're in a Cartesian coordinate system, X, Y, just like high school math, geometry, stuff like that. They're typical. We either index them from 0 to 255, because that fits in 1 byte and 8 bits, or 0 to 1 as a floating point. That is for those of us that are going to do more computational stuff. And I said earlier that you just basically need to check what library or framework you're using. All right, color images. Grayscale is cool, but we don't really live in a grayscale world. Like 0.01% of the population maybe, because they don't have short, medium, or long cones. But it's a sad existence. Well, I shouldn't say that. Maybe they have a different perceptual thing. We're going back to Nagel. All right, how did we do this like back in the day? Well, we gave it the old college try. And what we did was we created lenses that had basically 3 different filters. One would bring in a red channel, one would bring in a green channel, and one would be a blue channel. And wouldn't you know, when you stack them on top of each other, you get a color image. Quick question, do you think it matters what order you stack the bands? No? Yes? No? Hold that in your head, and then we'll come back to it later. So early cameras, like the lantern projector, that's what's going on. That's why it has 3 lenses, right? It's a goofy looking contraption, but it is able to do, color photography and color and film. Today we don't do that, right? Well, I'll say today we don't do that on the kind of cameras we use. For like industrial applications, sometimes it's really good to have one camera kind of dialed into one spectrum of light. If any of you go into like food production, you manage a food factory, there's a lot of this kind of stuff that goes on in terms of detecting like whether that meat is spoiled or not. So how does that work in a digital camera? Because we don't have 3 lenses. So we have basically 2 systems. One is the light comes in, it bounces off a mirror. We have a Canon in the Rhetoric Studio that we will take apart a little bit, take the lens off so you can see it. The light hits that, goes through like a pentaprism, similar to like what a submarine captain would look at. And that's what you see in the optical viewfinder when you look through. But then some of that light just passes straight through to go to the sensor, right? And then in mirrorless, a little bit newer, just goes straight there, and it's an electronic viewfinder that doesn't actually physically reflect the light. But in both cases, we have our focal length, which is the distance from our aperture to our sensor, and then we can adjust how much light gets in based on the aperture of the lens that we select and put on. And of course, things like the flange at 18 millimeters, that's like a fixed focal length. You can't like go any closer than that. So they of course have to model for that. Questions, comments? Cool. So how do we get color if we don't have 3, like the lantern projector, with something that, to be completely honest, I still have trouble understanding. It's trippy to me. But remember we talked about short, medium, and long cones? Which cones did we say we had the most of? Medium. We have most mediums.
What
Yeah.
is it, the green?
Yeah, we're very receptive to green yellow, right? So what the Bayer pattern does is it basically overlays these filters onto that sensor, that thing in the back that's being hit, and it's red, green, and blue because we know from last lecture we're going to use those primaries to make a lot of colors, but we give a lot more weight to the green filters on it because we're trying to literally approximate what happens to our eye. So yeah, Bayer pattern is pretty interesting. This is an example of the image where they've kind of overlaid the Bayer pattern that is literally on the camera sensor so you can see. To be honest, this still trips me out. I don't know why, and I can't explain it super well. There are some things in this class where I can be like, I can hold court on. The Bayer image filter and how we get RGB color from it is one that I still have a little trouble wrapping my head around. But we know theoretically why they've chosen it the way they have because of our propensity for medium cones and thus yellow-greenish vision. Because remember, it's not just red, green, and blue. It's this kind of spectrum. Questions, comments?
I remember from the reading.
Yeah.
It was saying that, like, to do the Bayer grid, it's like you take the grid and you do every other box, like half of it basically all green, and
Yeah.
then you fill in the red and blue, all like alternate each
Around it, yeah.
all around the grid.
Yeah, I think what I conceptually still gives me a little trouble is like how that's like physically is over the sensor and then how you get a full color image from it. I just need to like do a little more reading and be a professor there. All right, so we have, if we want a red and green image, now all we do is we take basically the equivalent of grayscale images, but in 3 dimensions. And instead of it being grayscale, it's grayscale relative to a given color. So this is the amount of red pixels that you turn on, this is the amount of green pixels that you turn on, and this is the amount of blue pixels. So now we have that kind of metaphor of like a robot who's turning dials. Now for every pixel, that robot needs to turn 3 dials. And they need to say, okay, right here, I need to turn the red up this much, the green down that much, and the blue this much. Does that make sense? So in each pixel on your screen, if it's a color display, it's got 3 different channels that you can manipulate. Yes, Ashford.
With the Bayer pattern, so that's like a literal like physical filter that they put in front of like a little sensor.
Yes. And we can see that we're trying to maximize our color space, right? And we know generally what the human eye is responsive to. So when we were designing LEDs to go in, screens, we tried to pick colors of LEDs that best matched the peak of our cone response. That makes sense, right? And then all we do is we take each one of the waveforms in our given image in terms of pixels, and we stack them on top of each other, and then we get this combined image. I spent way too much time making this slide. Does that make sense? We'll just watch it a little more.
It's pretty cool.
Yeah.
How did you do that?
You're going to do the exact same thing on Thursday. I coded it, and you're going to do the exact same thing. All right, so remember, there are a lot of different ways to represent color computationally, though. We have RGB decimal, right? So this would be like 65% on the red channel, 105% on the blue channel and green channel. Remember, this is going to go to 255 traditionally. We also have hue saturation value, which we're about to get into. But we have basically developed all these different types of ways of basically saying that a color is this numerical kind of array or fixture. I want to just hunt out hexadecimal color. If you guys ever do any like web design that you're shaking your head, where have you come across this?
Can't remember what I did, but like we had to look up like the hex colors of like different like logos.
Yeah.
Can't remember what.
Yeah. Really, really important graphic design and web design. So like you want to make sure that that version of red is always the exact same red. Just think about it in terms of a specific code and then access that code when you're working in Photoshop or you're coding up that website. You're shaking your head. I know you've done a little front end. You've been on front end design teams. And then CIE, we know what that is. We know where that's coming from. It's coming from that French organization. All right, so we can do some cool things in terms of translating from the RGB color space, which I think is very easy to understand with our long series of discussions about rosin codes, to something called hue saturation value, which is another way of thinking about color. So also spent way too much time making this slide. We could think about RGB colors as a 4-dimensional kind of space. And depending on the relationship between blue, red, and green, we get to inhabit different parts of the cube, right? Hue saturation value is also a 3-dimensional space, but it's more like a cylinder. And there are going to be some specific reasons why we might want to operate in HSV rather than RGB. So hue saturation value, just a little review. It's a different model based on the perception of light. And whereas RGB is like, you can think about a robot turning knobs, or literally like in grade school when you mix a couple primary colors together, that doesn't really tell you a whole lot about the luminosity, the brightness or lack of brightness in it. So hue saturation value also gets at the hue is the color, but the value is like how much black to white do you have in that color. So you're able to add 2 more dimensions. And it allows you to do some pretty cool things that range from Marvel movies to robotic systems. And since we have a combination of interests, I picked some examples of this. Yes?
Is there significant math reason behind why one's a cube and one's a cylinder?
Yeah, in fact, what are we looking at right now? All right, so this is another thing I spent too much time doing. This is showing you like physically how you translate geometrically from RGB to HSV. Then I'm going to show a little math for Jabba because he asked about it and I knew he would. And then we're going to leave the math alone and we're just going to look at what this looks like, okay? So this is literally, we're going from the 3-dimensional space to a smooth cylinder. So we start with that 3-dimensional cube, basically flip it so the black is on the bottom, and then we arrange the colors and we get to a cone. This is the math behind it. Does that make sense to you? Okay, well, I'm gonna give you, hang with me, and if the math doesn't make sense and you think you need to know it, we need to talk in office hours. Does that make sense? We have a set of real numbers that can take the values from 0 to 360. That's our hue. See 0 is there, 360 is there. Our saturation is a set of real numbers between 0 and 1. That's similar to like the pixel intensity. 0 is completely black, white, and then our value also a set of real numbers. To make the conversion, it's actually some very simple math. Okay? Ned.
On that one slide, it was like hue is what color, saturation is how much color. What was like the value on it? Like
Yeah.
how bright?
How bright? So this thing that I also spent a fair amount of time is literally doing the equation and switching it from RGB to hue saturation value. Does that make sense? So step 1, we get our value channel, we convert it, our saturation channel, and then our hue channel. This looks really trippy, doesn't it? Red, green, blue is easy to understand. This is way harder, I think, to conceptualize. So the hue is doing like all of our color. And then what is saturation again? Somebody remind me? How much? Of all of the colors you're seeing, how much of those colors are there? And then what is value?
How bright?
Yeah, and which makes sense because you see like this back one becomes basically a grayscale image because it's brightness. How many people are still having trouble wrapping their head around this? It's okay. I mean, it took me, honestly, years. Kind of, sort of? Yeah. We see that it can be done mathematically. We see that it's a different kind of color space in which we have the color, the basically amount of the color, and then the brightness of the color. But it's still a 3D tensor, right? It's still a 3-dimensional matrix stacked on top of each other. That hasn't changed at all, right? It's just a different kind of representation of color, okay? So why would we, this is easy. This seems a little conceptually more difficult. Why the fuck would we deal with it? Well, because you can do some really cool things with it. So one thing you could do is you could take your saturation channel and you can boost the saturation. So here, not a very saturated image of color, right? This is our color, this is how much color. You see I add more color to it by making it lighter, and now I get a pop here, right? You could also lighten or darken the image by taking the last channel, now this is the brightness of it, pretty dark, and then I basically adjust those pixel values, and now I get a lighter image. These are things that are harder to do in RGB. Does that make sense? Now, now you feel more comfortable now? Good. So that's my only desire in life, is that you guys are feeling comfortable with the content. We could also, of course, just shift the colors, right, by shifting our hue channel, our color channel. You see how this is starting to threshold certain objects just based on color? Yeah. And you can make some pretty goofy things here, right? This is Patrick about to put in the buoy for the project that I'm working on him with. These buoys are cool. They are attached to the Iridium satellite network, which is the same thing that Garmin's use. And so you can check to see what the conditions are like from your house before you go out, because this is the Bering Sea, and we're like 60 miles, or we're like 30 miles out in a boat that's like from here to the wall, right? And so it's really important for UPIC people to be able to take that traditional knowledge and then also augment it with like accurate weather forecasting, which for them is like waves are the most important thing. They're a seafaring people. All right, or you could do just like stupid stuff. Like you could just say, you know what, I really like this hue. So let me just give the whole image kind of that hue. And there we would just multiply the existing value, like literally multiply it by our hue channel at every pixel, do that multiplication, not change saturation or value, and now you get this like really trippy thing. Looks like a Jimi Hendrix cover or something like that. Yes?
So if you want to get the same effect with RGB, you have to change every single pixel.
It'd be very complicated. Yeah, can be done. Easier mathematically and computationally to just convert it into a different color space and roll. All right, or a pattern like a rainbow for some reason, or you wanted to put a pattern of like stars, you could do that too. Multiply it out. You can also increase and threshold the saturation. So now we're not just increasing, we're having a very simple algorithm that says any threshold value over 0.03 in that pixel, keep it, everything else get rid of it. We're making an either or kind of decision. And that will start to be able to then just do certain parts of the image. So basically we're just increasing the saturation of colors around Patrick here. See this in Photoshop a lot. Yes?
No, good question.
Yeah, and then we can develop mass out of that and go that way. So let's look at some applications of this. One is social media filters, right? Things like Instagram make a lot of money basically on being able to network photos, but also just do simple things like this in a hue saturation value space. Another application, color grading in movies, right? This is where manipulating hue saturation value to go from this, which is shot in the camera, to something like this that looks quote unquote better. You see, yeah, color.
For that one, would
Yeah.
that be considered, like you would be changing the value in that one? Because it's like
Probably a little of all.
all?
Yeah, it's like, again, like you're manipulating each one of these things to make it. Saturation is obviously pop there because the colors like pop more, but it's probably all three. Color grading is a huge part of movies. It's from Moonlight. Schindler's List has like a very good classic thresholding where they threshold just that coat and then boost the saturation of everything else almost down to grayscale. Directors like Wes Anderson, color grading is a huge part of how they kind of get their place in being in the world. And we live in a world in which filters can make you a lot of money, right? Just that. But there are some other applications for the things like object detection, like that rifle detector. It's really takes a lot of time to go through and label each rifle, because that's literally what you do. You label a bunch of phenomena and then you feed it into a neural network. But I could just take that image, change the hue saturation value, and then the neural network will treat it as a different type of image and start to learn. So this is a vision or an example of this that I did for a project where there's a lot of random noise, but these are arrowheads, and I wanted to build like an arrowhead detector. And so each one of these, I basically copy and paste them onto a fake image with code, and I change the hue, saturation, and value. So I have now millions of examples to train on instead of like 30. You could do this. This is the, we then apply algorithms like this. This is one I made to do SpongeBob and Uluwaks. We could apply them to social media feeds. So this was a project I did as summer research with a student a couple years ago. The idea was like, can we go into TikTok, find a phenomenon, and then be able to monitor how much it is on TikTok by doing object detection? Now you're starting to see like that could be financially lucrative for certain things. And then in the domain of robotics, hue saturation values-based approaches for detecting objects are often the way that we do this. So we're in a factory or lab. We can standardize the incident light. We can, all the things that make it complicated, we can kind of lock down. So it's a conveyor belt. It's moving like, I don't know, cookies across. We can ensure that it has a certain Kelvin. We know that the cookies are always basically going to reflect the same incident light. They should be the same color. And then we can just use hue saturation value thresholding to decide what object we want to manipulate, then take that 2D image, reproject it into a 3D coordinate system so that the robot can grasp it. Right? This is cool for a number of reasons. One of them being that it's like, you're going to do this exact thing on Thursday. One of the pictures I'm going to have you do, you're going to take a picture of something that has color on a neutral background, and you're going to use the exact same algorithm as him to be able to do an object detector on it. We're always looking for very simple algorithms like that don't require like millions of items of training, but you have to understand no free lunch. This is a system that is very tailored to the fact that you can control almost all of the properties about lights and cameras to your design. That is going to be different than an object detector that's embedded in a camera doorbell system in which you can't. Because you're going to have sunlight, you're going to have shade, you have all these different types of albedo and reflectance values. But hue saturation value based thresholding and detecting is definitely a big thing. We're at 11:19. I got us done a minute before class is over. Do we have any questions? Ashford.
With the flat color, before it was color graded, that started foreign motion.
Yeah.
So I've heard that like shooting in flat color is better, right?